Okay, so my name is Daniel Sayed, and this is the problem of the week for Pascal's triangle. So I wanted to go ahead and talk about what really is Pascal's triangle. Now, if you look on Google, it says that it's a triangular array of binomial coefficients, but I think a much simpler and more understandable explanation is that it's essentially an infinite triangle of numbers where each number would be the addition of the two numbers above it. So to clarify really what that means is really has to do with how you compute this entire triangle, right? So focusing a bit more on the infinite aspect of this, when you have, like, say, for example, this 3 here, the two numbers above it are 1 and 2. So when you add them together, it equals 3. And then we can take 6, for example, where you have 3 plus 3 equals 6. And this can really apply for any number, right? 35, add 15 and 25, and you get this number. And really, that's the main way you compute Pascal's triangle. And if you're curious on the ones on the side and how they're added to, I guess, I believe you could imagine a 0 here. And this only applies to the addition part of this, but you could apply an imaginary 0 here to, say, that's what it's being added to if you really wanted to. But otherwise, just assume that the very ending rows of each side or diagonals are just going to be 1s. And then everything in between is the addition of the two numbers above it. And that's really on how it's computed. But the next thing I want to talk about is really some interesting facts about the Pascal's triangle. So I have it. I have the first 10 rows of the Pascal triangle listed right here. And first thing I want to say is the sum of each of these rows is actually a power of 2. So the first is 1, so that's the sum of the first row. The next one is 2. The next one is 4. And I'll just go up to this one because the numbers do get fairly large after a certain point. So I think I'll just go down to maybe 10, 14, 16. Okay, I'll go down to this one. So this, since the way the Pascal's triangles works is that the number of rows actually starts off with 0. So when we want to see how this is a power of 2, you have to start off by 2 to the power of whatever row you're on. So we'll assume that the row is equal to n, right? So 2 to the nth row would give you the power of that row. So if this is row 0, then putting a 2 to the 0th power would give you 1. That's the sum of this row. And this could apply as you go down 2 to the power of 1, the first row, 2. And so on and so forth for the second row, which equals 4, 2 to the power of 3, which equals 8, and of course 2 to the power of 4, which equals 16. And on that logic, if this one is going to be equal to 32, and so on and so forth. That's the first interesting factoid about that, I guess. The next thing is that there's a pattern that all of these rows follows, not counting these 1 rows. So this, excluding this row, this second row right here, this diagonal, is actually a bunch of counting numbers, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9. And then past that, we start to get into a bit more of like shapes. So this is all triangular numbers, this row, diagonal right here. And what I mean by triangular numbers is, like take 3, for instance, right? In order to make a triangle, you would have 3 points, something like this. And then if you wanted to make a bigger one, you'd go like this, and now you have 6 points, and so on and so forth. You couldn't make a triangle that's like this, that you would need a point here. So this would be 9 points, and you would put a 10th, and that would be this one. So that's how the triangular row diagonal works. And then as you continue on, this is tetrahedral numbers. This is pentatope numbers, I believe. And basically, those are like fancy terms for, just imagine this sort of pattern applied to three-dimensional shapes, and you sort of understand what happens as you progress through this. And each three-dimensional shape is also like has the number of sides that represents the row, right? So if it's a tetrahedron, it's the fourth diagonal. Then if it's a pentatope, then it's the fifth diagonal, and so on and so forth. And then one final thing is that if we look at diagonals in the sense that each diagonal ends with a 1, and starts with a 1, right? So this first diagonal, right, we get 1. And then sort of hard to see this here because of the way this is like, it's on a piece of paper, but to be more clear, if this is how the second diagonal would look like, okay? This would be 1, and then the next one would go like this, that would be 2. The next one would go like right here, that would be 3. And the next one, I know it's a bit hard, but it would essentially be this. And then I'll just do one more, I believe this. So that would give me 8. So if we take this sequence for a bit more clarity and put it up here, or to the side, I guess, somewhere, 1, 1, 2, 3, 5, 8. So I took the additions of all of these rows and or diagonals, and I would just put them here for clarity. So what's interesting, this is actually the Fibonacci sequence. And essentially this sequence is defined by the two numbers, the two first numbers that come essentially add up to this one. So 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, so on and so forth. And those are just some interesting facts about the Pascal's triangle. Now, the second thing, the third thing I want to go ahead and look at is really the relationship of Pascal's triangle to combinations. So, essentially, Pascal's triangle will allow you to answer like how many different ways can something happen, or more clearly, how many combinations of a certain outcome can occur. So, to put that into with an example perspective, right? Let's take coins, right? Say you have 7 coins. I believe that's 7. 1, 2, 3, 4, 5, 6. Yeah, that's 7 coins. And you're wondering how many times or how many different ways you can get 3 heads, right? 3 heads. And so just to clarify what that means, right? One combination would be in order in where you would flip all of these coins and you'd get 3 heads. So you could put a head here, maybe you'd get a head here and then a head here, or a head on your first, try a tails on the second, and then something like this could be a combination. But the just as likely this is also. So something like this, right, has 3 heads. So what Pascal's triangle will determine for us is how many of these different sorts of orders, or for more better terminology, combinations, are actually possible. And the way that this is done has to do again with really the rows and how everything is. So an important thing about Pascal's triangle is that the first row is always the 0th row. And what we want to do to figure out how many combinations there are, just to clarify, the combinations that we are looking for is how many combinations of 3 heads are there if I flip 7 coins. So what we want to do is essentially figure out how many tests or coins, I guess, do you have, right? So I have 7. So we go down to the 7th row, okay? And we have to go to the basically 3rd one down. But like I said before, we have to start with 0 in the Pascal triangle. So this would be 0, and then 1, 2, 3. So why does that really make sense, right? Basically, it shows a bit more of like, so, okay, let me put this into a bit more clear perspective, right? When you do this, a combination is typically defined as like, in a calculator, for instance, it would be like 7 choose, oh, sorry, this is a bit big. 7 choose 3, right? So when you do this, you take the row that you have, you put 7, choose, and then whatever, like, we can assume these like columns, right? Like this. So this is the 0th column, the 1st, the 2nd, and the 3rd, right? So this is the 0th, we'll assume column. This is 7 choose 0. That'll give you 1. What that really means is that if you have 7 coins and I want 1 heads, how many combinations are there? Well, there would be 1, right? Oh, sorry. If you have, this actually means if you have 7 coins and you want 0, I forgot, is 0 heads, how many combinations are there? Well, there would be 1 because, there's only 1 combination in where you wouldn't have any heads. That would be when you had all tails. And that sort of just transfers over to the next one, right? Where it's 7, again, choose, this is the first column, so 7 choose 1. And you sort of see the pattern here. And basically, we can get to the 0, 1st, 2nd, and 3rd. So basically, this is 7 choose 3rds equivalent. And we can confirm this on our calculator over here. So 7, go here, choose 3, should be 35. That's exactly what the combinations is. It basically tells us how many combinations of a certain outcome can occur. And this really applies not just to like heads or tails, but to really anything where you have 2 ways to go, right? Heads or tails or yes or no or something like that. And that's really how it applies to combinations. Now, finally, I want to go ahead and talk about how Pascal's triangle really can be used to expand binomials. And for example, we'll take x plus y to the power of 4. So the binomial theorem is basically x plus y to the power of n. And in context of the Pascal's triangle, I know it's a bit muddled up here, but just bear with me, I guess. This tells us how what coefficients are going to come when this binomial is expanded. So that may be a bit confusing, so let me put it in a bit more clearer terms. If we have x plus y to the power of 2, for instance, this would then be x plus y as so. And then, this would, of course, become this. And I could just do the computation for you, I guess. And this is what it would come out to. So if this is what it comes out to, what happens is that the coefficient is a 1 here, a 2 here, and a 1 here. Now, this was a very simple example, but these are considered binomial coefficients, by the way. The coefficients of the expanded binomial, right? So that's 1, 2, and 1, right? So this was a very simple example, but when we have larger powers, like let's say 4, right, it would become a lot more difficult to multiply over and over again x plus y, and it would be a lot simpler to just figure out the binomial coefficients and just plug them in accordingly. So that's what Pascal's triangle allows us to do. So back to our example of x plus y to the power of 4. So if you remember back, we actually made the rows equal n. So when we want to figure out something like this, we can pick n, the number of the exponent here, and go to that row. So let's make it a simpler explanation, or a clearer explanation. Before I continue on to the 4 example, we can use the 2, right? Because we already expanded this. So we know that the binomial coefficients are 1, 2, and 1 again, okay, in that order. So if that's the case, we want to go to the second row of Pascal's triangle right here. And if we look past the scratch marks that I put, it is indeed 1, 2, and 1. Exactly what we have here. So now, of course, logically speaking, as we have more binomials, there are going to be more like variables. So there's going to be like x plus 4 plus like x3 and so on and so forth. Like there will be more of these variables, and there won't just be 3, right? So there'll be like 4, 5, 6. So what this Pascal's triangle tells us is that if we go to the 4th row in the triangle, if we go here, then the binomial coefficients, or all the numbers that would essentially go in front of the variables when expanding this binomial expression, would be in this order: 1, 4, 6, 4, 1.